So we've looked at some very simple molecules with the helium and the hydrogen and their ions. We were only dealing with those sigma. Now remember from valence bond theory we talked about sigma and pi. We're going to talk about the same thing here when we look at molecular orbitals. We're going to follow the exact same rules that we did for electron configurations. So we had the alpha, we fill from the bottom up. We continue filling as we add more electrons. Pauli exclusion principle, still a maximum of 2 electrons per orbital. Hund's rule, which is our cookie sharing rule, everybody gets 1 before anybody gets 2 in our degenerate orbitals. And to make things a little bit simpler, you can look at all of the electrons. We're only going to look at the, like up to the second row, but you can also look at just those valence electrons, because when we start to look at the core electrons, we're going to have the same number in bonding and antibonding. The only real difference we come upon is when we start to look at those valence electrons. So we actually have a way of evaluating kind of the relative stability of a particular molecule. So you'll see we've got the H2 that we had before and helium-2, and we also have a couple of ions in here as well with the helium-2 plus, which we saw, and then the H2 plus. And what we want to look at is something called bond order, because just like we had formal charge to help us figure out what the most stable Lewis structure was, we can look at bond order to help us figure out what the best, or whether a molecule is going to be stable. And if we actually get a bond order of 0, like we will for helium, means that molecule doesn't exist, so we're going to have an unstable compound. So apologies, some things got a little out of line here when I imported this picture. So, but you can see that it goes with our, this goes with that. Kind of line up those rows there. And so what we look at is for bond order, we say 1/2 times the difference of the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals. So if I go back to that picture on the previous slide, what I look at is for H2 plus, we had 1 electron in a bonding orbital, no electrons in antibonding orbitals, so 1 minus 0 is 1, divided by 2 or multiplied by half, either way, we get 1/2. When I look at H2, I get 2 minus 0 divided by 2 is 1. For helium-2 plus, I get 2 minus 1 is 1 divided by 2 is a half. And then for helium, I get 2 minus 2 is 0, so regardless of what I multiply it by, I still get 0. And what we see is that helium-2 doesn't exist, while as H2 can exist, as can H2 plus and He2 plus, the H2 is clearly the most stable of these 4 options. Now we're going to go on to look at the second period. So these are again homonuclear, which means same nucleus, so both elements are the same. We're not going to look at any heteronuclear diatomics. And so we look here with our lithium, and what we know is that with lithium, if we looked at all the electrons, we have our 1s and our 2s electrons in lithium. And so, but you'll see that really the only part we're interested in is what's up here at the top. This is the valence electrons. When we look at those core electrons, what we're seeing is that the bonding and antibonding effects basically cancel each other out. What we're really concerned about are the valence. So if I look at just the 2s, I get my sigma 2s and my sigma star 2s, and so I get 2 electrons in my bonding orbitals. If I just look at this versus 0 there, so I get a bond order of 1. Notice that if I looked at the bond order for looking at all of the electrons, I'd have 4 electrons in bonding orbitals, 2 electrons in antibonding, so that's 4 minus 2 is 2, divided by 2 is 1. So I still get the same bonding order regardless of whether I look at just the valence or look at the entire molecule. So what you see here is actually what happens when we look at our elements in that 2p block. So boron, carbon, nitrogen, oxygen, fluorine, and neon. So when I look at these, what I see is there's actually some differences between them. So notice here that the sigma s and the sigma star s, or the 2s, are exactly the same. Notice we're not looking at those core electrons, the 1s. We're just looking at the valence. So we're starting here with the 2s. We could also draw something very similar to this for the 1s, but it would be obviously completely filled. Then I'm going to go up here to the 2p orbitals and look at what's going on there. And this is where I notice the difference. I'm actually going to start at the top where there's no difference. So we have the sigma star 2p. We have the pi star 2p on both, and then we have the pi 2p and the sigma 2p here. So we see a difference. Basically, these are flip-flopped, and we're not going to get into why. That goes kind of beyond the scope of this course, but you do need to recognize that they are different from one another. These are all bonding orbitals. We now have degenerate orbitals here when I look at the pi 2p. So when I think about Hund's rule, I'm going to have to put one electron here and then another electron there before any pairing begins. And that's where we see what's happening with oxygen. So if I look at oxygen, we have those 6 valence electrons in each oxygen, which means I'm going to have 12 valence electrons total in the O2 molecule. And so I can actually start putting those electrons in. So I can say 1, 2, 3, 4, 5, 6. There's no degenerate, so I can fill that first. And then I'm going to start in with the pi orbital here, the bonding orbital. So I go 7, 8, 9, 10, and then 11, 12. So even though based on the Lewis structure we predicted that this would be diamagnetic, what we see based on experimental data, and MO theory agrees with that, is that oxygen is actually paramagnetic, that it has unpaired electrons. Notice that this model, this pattern, goes for having oxygen, fluorine, and neon. If I have boron, carbon, and nitrogen, we follow the other pattern. And these are the only elements we'll be looking at. We would see similar trends when we went on down to the third row, but we're only worrying about these particular elements and only worrying about the homonuclear. We will not look at any mixtures where we have like boron and carbon or even splitting up nitrogen and oxygen. There are other issues at play to figure out which model we use in those cases, but we're always going to be looking at these homonuclear diatomics. But what we can do is say, okay, what if instead of having O2, I have O2 with a minus charge? What's that going to look like? Well, we're adding an electron, and so we would just be adding an additional electron here, still having a paramagnetic species because we have an unpaired electron. So the ion will follow the same pattern as the neutral molecule. So what we have here, if you go through and draw all of the diagrams for all of the neutral molecules from lithium up through fluorine, we can see we've got some bond orders here. And so the most stable of these is going to be nitrogen because it has a bond order of 3. Oxygen and carbon are coming in as close second at bond orders of 2. Lithium, boron, and fluorine all have bond orders of 1. So respectable, but not the strongest. And what we can see is the correlation between the bond length and the bond order. So notice that nitrogen has the highest bond order, it has the lowest bond length. That means the atoms are as close together or closer together there than they are in either the carbon or the oxygen, where the bond order is lower. So as the bond order increases, so bond order increases, the bond length is decreasing. Same thing with our bond energy, we can see a trend there as the bond order goes up, so we go up through nitrogen, the bond lengthens, we also see that the bond energy is increasing. So the higher the bond order, the shorter the bond, the higher the energy of that bond. And we can do this in neutral molecules or comparing ions, just like we did with the hydrogen and the helium. We had the hydrogen ion and the helium ion. We can do the same thing with all of these species as well.